Hello, this is your teacher Todd. We're on to chapter 2. Now this is Todd Lamley's CompTIA network material, and I'm going to give the presentation because I'm your instructor. So let's get on to it, and we're going to talk about OSI specifications. There we go. Let's talk about the objectives. Well, down here we see the objectives, and it's part of the CompTIA objectives as well. So as you study this, you get closer and closer to a CompTIA Network Plus certification. That's awesome. Now what we have here is that we're just going to learn about the OSI model. Now there's 7 layers, as you can see. Here we're going to start listing them from the top. Is layer 1 physical, data link, network transport, etc. But a lot of times we flip it around because we like to say the application is on top of the world. It's at the highest level. So let's go ahead. We're going to talk about internetworking models. Now there's different models. There's the OSI model, and there's also the TCP/IP DoD model. So let's talk about the OSI model first. What is it we're trying to do here? Well, it was in the late 1970s when this reference model was created, and what they're trying to do is to allow us to have interoperability between different vendors' equipment and software, etc., etc. And I'm going to get into that. So as we can see on the second point, it's to help vendors create interoperable products like network devices, hubs, switches, routers, etc., etc. And it's actually interesting because this was a model, an architecture, and the architecture and the model we use today to explain networking and to talk about it and to understand it. But what's interesting is we don't use the OSI protocol suite because they actually had protocols that went along with their model. So we're using their model, but we're using the TCP/IP protocol suite. So, but in any case, what it does is it breaks up the big problem of networking, and it breaks it up into smaller, manageable chunks. And then we try to define how those chunks are and how they interface with other chunks, and then we can have interoperable products. As long as 2 vendors implement the same chunk, there's a standard that says how to implement that, and then we're guaranteed it will be interoperable with other products. And again, I'm going to get into detail on this. So what are the advantages of the reference models? And what I like to do is I always like to start and spin it the other way around. What would the world be like if we did not have these models? Well, if you're a home network user and you've been using the network for a long time ago you might have been using the speed of Ethernet 10 megabits. And then after that, after a while, you might have been using 100 megabits. Well, today all network cards, just about all network cards, are gigabit. They can operate at gigabit. They can also drop down to lower speeds. But we have the speeds 10 megabits, 100 megabits, a gigabit. Servers can run 10 gigabit. And here's the problem I'm trying to show you. What would happen if you went to the store and you wanted to buy network cards for your PCs if it wasn't built in, and you bought a network card, and the person at the counter said, well, what speed do you want? Well, today what you'd say is, I want a gigabit, but of course I want to be able to drop it down to 100 meg or maybe 10 meg also. What if the person at the counter said, well, we don't have that. What we have is we have one product that's a gigabit, but it's a gigabit and it drops down to 500 megabits. And you say, well, what if I want to drop down to 100 megabits? And they can say, oh, I've got a product for you. It's 100 megabits, but it drops down to 50 megabits. And you say, well, what if I want, oh no, what happens if I want to connect to a device that runs 100 megabit and I want to connect the next week to a device that's a gigabit? What do I do? And the salesman said, oh, it's no problem at all. You just buy both of them. And then when you switch speeds, you switch hardware cards. Well, that might be all great, but what if you later on the next year they went out of business and you were running it at speeds like you were running at 500 megabits, and then they went out of business, that vendor that you had the card with, and the new vendor had 600 megabits and 700, but they didn't have gigabit. Okay, that's it. You understand now. The problem is just a nightmare. So it's so cool that we have these standards so that the speeds are 100 megabit, a gigabit, and 10 gigabit. There is no other standard speed, and that's because we have these OSI reference models and we have standards which specify exactly what speeds they're allowed to use. It also means that, could you imagine this? What if you had 100 megabits and you connect to a switch and it doesn't work, and you go to the vendor, and what if the vendor told you, oh, well, on your PC the Ethernet card you're using is from Dell and the switch is from the vendor HP. You have to use the same vendor. You can only go from Dell to Dell or HP to HP. You would just be having a heart attack, especially if you have all this HP and then HP goes out of business. So that is the beauty of the reference models and the standards and the multi-vendor interoperability. It's awesome. We take it for granted, but I think I've drilled in the point to you. Maybe harder than I needed to, but here we go. So that is it, and it also makes troubleshooting easier as well. And you can swap out one card and put another card from any vendor, and you're guaranteed interoperability. It's just fabulous for us. So look at this. It's flipped on its head. Before, in the first slide, it was the opposite way. At the top, we had physical data link network. Well, that's okay because we were counting 1, 2, 3, 4, 5, 6, 7. But again, we flipped it on its head, and we have the application at the top of the world. And think of this. Above the application layer, we've got the email program, we got the web browser, whatever. And they talk to the application layer, and then we have all this magic down below, and sooner or later they're going to communicate with the web server. Now, the way we divide these OSI layers up is we've got a bunch at the top. We got the application presentation session. The application, what's all that about? Well, we have these application protocols for printing and for files, for messaging, database. There's a whole bunch of application database standards. You've heard of SQL. There's other application services as well. Now check this out. Look at the presentation layer. Look at that. It has data encryption and compression. Think of it. It's a service to the application. It's a service, meaning if you wanted to write your own program, let's say a web browser, and you wanted to do encryption, you don't actually have to go to the drawing board and try to write all the encryption into your web browser. You don't have to do that. All you do is you make a magic service call, and you put in a request, and you say, I want to have all of the data encrypted between the client and the server. And magically, it's all done. Okay, well that sounds pretty good, but let's take it to the next level. Come on, let's move it up a notch. Not only can you do that, but I just gave you an example where you have a web browser using encryption, and you have all this encryption. You didn't even have to write a program for it. You just call the service. Well, the same thing goes if you have an email program. Yep. If you have an email program, you make the same similar call, you just request encryption, and bingo, everything is encrypted. Even though in your email program and in your web browser program, you never wrote any encryption. Now think of this problem. Let's suppose that there were 1,000 vendors who write encryption, and they all had their own special proprietary encryption way. Well, that would be a problem, because when your email program or web service tries to call encryption, you're forced to choose one of those ways. And what if the application on the other side doesn't support the same encryption standard? Uh-oh. Problem. Major problem. So you'd have to coordinate with them. And it would just be a nightmare. It would never work. So that is what we're trying to solve. We're trying to have these standards which say for encryption, there's these 10 different ways to do it. This is how you invoke the service. And as long as the web client and the web server are using the same standard encryption, the same choice, it's going to work together. Even if it's completely different vendors. You might have like Apache web server on one side and some kind of encryption there, and you might have Firefox and maybe another vendor has written the encryption, but as long as they agree upon the standards, everything works together. So that's the beauty of dividing things into layers and to have standards for the different services being offered. Now we have the same thing with compression. I've written some web stuff myself. I wrote a web robot, and I was decompressing the compressed data from the web server, and I just call this standard service, and voila, everything's automatic. It's not like I have to write all the code myself to do compression. So there's other services too, like translation, but I won't go into details. And the session, think of it like a telephone call where we're making a phone call, we set up a session, and we're good to go. And the transport layer, you see there's a little gap here. We're into something different. And the transport is end-to-end connection. And what we mean by end-to-end is the transport address is the address of the service, or for example the web server, on the remote end. We might have on the same server, we might have a web server, we might have a database server, and we might have an email server, right? Well, when the remote machine gets the traffic, when the server gets the traffic, how does it know, should I send it to the email server program? Should I send it to the database? Where do I send it? And the way it knows is it looks at the transport address. That's right. So it's the transport address which says when you get to the other server, send it to the web server. That's how we do it. On the other hand, like I said before, the network address is only concerned to get the message to the server. So once it gets to the server, what does it do? We need to look at the transport, and then the operating system gives it to the correct program or service. So that's how that works. Now the data link. Let's talk about the data link. That does framing. I mean, we have to send these digital impulses, which is the physical layer, like ones and a zero that could be a different voltage. But what we do is we break all that up and we put it into a data link frame. And in the data link frame, one of the things we have is the destination address on our local network. And once again, if we're going to go from the data link and we're trying to get to a let's say a Cisco server, and you're home, you cannot send it directly to the Cisco server by putting in the Cisco data link address. That's right. You have to put the Cisco IP address up here in the network layer. And instead of putting the Ethernet MAC address of the remote server at Cisco, you put in this data link destination address, you put the destination MAC address of your local router. That's right. So at the data link, we put the address of our local router. At the network, we put the IP address of the Cisco web server. And at the transport layer, we put in something like 80, which is the magic number to go to a web server once it hits the Cisco. We kind of worked our way all the way down here, right? We got into the framing, but there's the physical. And the physical basically takes the data link frame and it converts it into a bunch of ones and zeros. Really boring. But we do have to have a standard for the ones and zeros. We have to make sure that when one Ethernet adapter sends traffic, and when it uses ones and zeros, we have to make sure that the receiving Ethernet interface is using the same standard. We couldn't have like 5 volts, we're going to send a 1, and then another vendor says it's a minus 5 volts, it's going to receive a 1. No, we need these standards between hundreds and hundreds and perhaps thousands of vendors so that we all have the same standard as exactly how you represent a 1 and a 0. And we also need cabling, we need connectors, and all of those standards like cabling, connector, 1 zeros, voltage, all of that is down here and it's done for us. And that's really cool because then we can take a cable out of our network, we throw it away, we put in a new cable, we go to the store and we say we want to get a cable, we want a Cat 6A, and that's it. And then the person in the store goes, okay, here you go. But can you imagine without standards? Oh, I want to get a cable. Oh, what speed do you want? Well, of course I want a gig or 10 gig. Well, okay, let's talk about a gig. You want a gig. Now, what vendors do you want to go between? What are you talking about? Oh, well, I want to go between... Okay, if you really want to know, I want to go between Dell and HP. And then they say, okay, here's a cable you need. It's a special cable, and it works between Dell and HP. And then you go, okay, but I also want to go between Dell and Cisco. And they say, oh boy, you can't do that. If you want to go between Dell and Cisco, there just doesn't exist a cable. What a nightmare. So it's just a beautiful world because we have standards, and you just say Cat 6E or 6A, 5E, 6, 6A, and they're just going to go, okay, here you go. And they do not care what vendor you are going to use for your network interface card or for your router or switch. They just don't care, because when you say the magic standard, then we just know it's going to work with all vendors because all vendors implement the standards. So that's kind of how it works. So I'm going on a lot, but it's very important for you to get these points here. So let's talk about the upper layers in a little more detail. So the application provides a user interface, and by user interface we mean the following. We got this application, it's an email program, and the email program will use this magic standard to communicate with the application. It's an interface. When we go up and down this way, what do we use? We use the term interface. Now what happens when we go between a client and a server and we're talking logical communication between them? This is a protocol. That's right. That's when we talk protocols. Horizontal. But if we go up and down, it's a totally different matter. Then we talk interfaces, and that's why we have the word interface here, because we're talking up and down. The application goes down to talk to the interface, and the presentation has its own interface, etc. Then we go to the session interface. But what happens if we are talking about the logical communication between two machines via the transport layer? That's right. Then we say the word protocol. So that's the difference between protocol and interface. Now, the application works basically with the application layer, and it has a few options if it's going to do compression or encryption for the presentation. And then a lot of magic happens. So this magic email program will take this big email message, and it's going to send it down the protocol stack, and it just keeps going down. Maybe it's going to be encrypted, maybe it's not. It's going to keep going down. It's going to hit the transport, and then the transport is going to say, you know, that's a pretty big email there. I got some news for you, application, Mr. Email Application. I got some news for you. The email message you want to send will not fit into the data link frames. And here's the coolest part. The transport layer doesn't even tell the application that. And the application doesn't need to know how big, how many bytes we can have in this data link frame. It doesn't know, and it doesn't care. And here's why. It's this transport layer that takes the big email message and breaks it into little pieces so that they're all going to fit across the network and the data link. It's just so nice for us. And that's part of the great thing about these interfaces and these services. We can be someone who is not the best programmer in the world, but the good news is if we write a web browser application or an email application, we do not need to be experts at how to do encryption. We do not need to understand how to break a big email into lots of different segments. We don't really care when we write the program if we're going to go over 10 megabit, 100 megabit, gigabit, or even instead of Ethernet, maybe we're going to go over wireless, we're going to go over token ring, we're going to go over Bluetooth. It does not matter. This magic layer architecture takes care of all those problems for us. And the way it does it is it has a whole bunch of restrictions. And as long as all the vendors obey the restrictions, otherwise known as protocols, then everything is going to work great. So there you go. So the session helps keep the application's data separate. And remember, it's the transport destination address which determines if it's going to go to the server's email server service or maybe it's database service. So that's the upper layers. Now the lower layers, let's talk a little bit more. The transport layer has this really cool feature. It can provide reliable or unreliable delivery. Let's talk about reliable because that's really cool. What the transport does is helps guarantee that if the client sends a message to the server, that we can be guaranteed, the application can be guaranteed it will arrive there. Now let's try to take an example, an analogy I call it. The analogy I'd like you to think about is the following. Let's suppose you are at home and you want to have the same thing. You want to have like a transport and you want to have a reliable delivery of a message, but you're going to use a post office. Here's what you do. One thing you could do is like you write something by hand, you put it in an envelope, you put it into the post office box, and you cross your fingers and hope it gets there. And most of the time it'll get there, but it has happened that things disappear in the mail. That's right. And that example is unreliable. Now let me show you how to make it reliable with a post office. With the post office, what you could do is after you write the letter by hand, here's what you do. You make a copy of it. You could make a photocopy of it. You could copy it by hand. And then you take one of the two and you throw it in the mail. And it goes to the remote destination. And you put in your letter. You say, I want it to be reliably received at your destination. So when you receive it, I want you to send me back a message. Or you just tell the post office, when they receive it, I want you to give me a message saying it got there. And then you send a letter and you wait and you wait. That's called setting a timer. The computer set a timer. They don't wait forever, but they set a timer, and you might set a timer. You might say, if I don't hear back from the post office in 10 days or maybe 10 weeks, it doesn't matter. You set some timer and you say, if that doesn't happen, I'm going to send the letter again. And when you send the letter again, what do? You make another copy of it just in case it's lost. You send it off and you start your timer again. And you just keep doing that. And that is called reliable transport. And that's exactly what the transport layer does. It has a copy of a segment that it's going to send. And it makes a copy. It holds a copy of it. And it only sends one of them. Think of it that way. It sends one of them. It sets its timer. Not for 10 weeks, pretty quick, maybe like 10 seconds or whatever. And then if it doesn't get an acknowledgement back that it was received, it makes another copy and it sends it through. And it does it again and again and again. And that's what we mean by providing a reliable delivery at the transport layer. Let me also tell you that for email and web traffic, we normally use TCP, and TCP is what we call that transport layer that's reliable. Now, that's not the only way to send data. Let's suppose you're into gaming, and you're like a gaming animal, and all you care about is the number of milliseconds that you have to wait before you see part of your opponent's screen. Now, in that case, when you're worried about, you're a fanatic, you're crazy, you run around and you sleep and you think all day long about microseconds. If that's you, I'll just tell you right now, this reliable service, it might be reliable and retransmit, but the problem is when things are lost, it can slow down. And I know if you're a gamer, you're probably like freaking out saying, I can't handle this, I can't sleep. What do I do? Oh, let me tell you what you do. There's something called an unreliable delivery. It's another protocol, and it's called UDP. And if you're a gamer, then if you use UDP when you're developing games, then things are like so incredibly fast. And you might say, well, UDP is not reliable. What if something is lost? And the gamer might say, I don't care if like a couple of pixels on the screen are lost. I don't care. I just want to see if that bullet's coming for my head, and if it is, I'm going to duck. So that's unreliable. So you have both. In the transport layer, you choose. Now, here's something interesting. It doesn't matter if we use reliable delivery or unreliable. Sooner or later, the transport sends this message down to the network layer, and guess what? This network layer doesn't need to know anything about if it's reliable or unreliable. It does not care. It does not look in the field. The network layer programmers didn't program about it. All they care about is one thing. Give me a segment, give me a destination IP address, and I'll do my best to help you get it there. That's the network layer. It does not care if you're a gamer or if you want reliable delivery. It just does its thing. Now, again, the transport, we've got the network, we have this transport address of the web server, which is port 80, or maybe of an email server. And then at the network layer, once again, we have the IP address of the server itself. It only gets it to the server. And then at the server, it looks at the transport. That's why, I mean, in the book they call it logical addressing, but you know what? I think my example is better than the book. Forget about logical addressing. If you're on a PC, you're web surfing to Cisco, the network layer destination address is the Cisco server IP address, only to the server, nothing more, nothing less. And then what the routers do, they're really cool. They have these routing tables, and you give them traffic to go anywhere in the world, and these routers, they talk to each other and they figure it out and they know how to get there. They're just really awesome. And they do that for path determination to go from the client to the server. And that's what we mean by end-to-end or logical. I mean, that's what we mean by logical addressing. But if you want to go to the application on the remote destination server, then you need, again, the transport address. Now, we've got the transport address. We've got the network address. Do we really need this data link address? And I'll just tell you the answer is yes. Even though at the network layer we have the big C, it's the IP address of the Cisco server. At the data link layer at home, you don't put the MAC address or the data link address of the Cisco server. You put it of your local router. I call it a router, but a NAT server might be a better way. But the data link is always local. You can only have a destination address of a machine on the same LAN you are on. So at home, that's why your PCs, no matter where they want to go in the world, at the data link layer, it's the destination of the router if they want to get on past the router to the ISP, etc. But again, your PC will put the destination network address of the Cisco server and then the destination port number, we call it port number, of the service, for example, the web service. And when it finally gets to the Cisco server, it'll look at the transport, it'll see a port 80, and it says, aha, that goes to my Apache web server. So that's all that stuff. Now, there is some error detection done at the data link layer. So if a bit is incorrect, it'll detect that. So that we have some of that. That's a new topic we're talking about. But we're talking about the MAC address. It's like the Ethernet address. And that's it. And sooner or later, we've got this big data link, and we've got this 48-bit address of the destination on the local network. That's the MAC address. How are we going to get it across this wire? Well, it's the physical layer. It's kind of a boring job. What it does is it takes the data, it converts it all into a bunch of ones and zeros, and then it has different voltage depending on if it's a 1 or a 0. It deals with the wire speed if we're going to go 10 meg, 100 meg, gigabit, or 10 gig. And it also specifies what the pinouts are of the cables, and that means if you have a cable and a connector, which wire goes to which connector pin. The answer to that, we look at the standards. It's part of the physical layer. Boy, I beat that to death. I'm sure you want to get to the next slide. Well, you're lucky, because we're talking about reliability. So again, that's the transport layer, TCP, reliable. Now what's it going to do? You just need to have this memorized. Connection oriented. That means it's going to find dropped packets, duplicate packets, out of order packets, and it will take care of it. Now, how can the client possibly know that the server received the information? Oh, it's easy. The server will send back an acknowledgement. It's just a special bit pattern, and it'll send it back, and then the client will say, aha, oh good, it was received. Now I'm going to send some more. Now, what happens if the client sends some transport segments, and that's just a magic word we use at the transport layer. We say transport segments, network packets, and we say data link frames. So segments, it's a transport layer. Now what happens if we send a segment and it's not acknowledged? Well, our timer goes off and we assume that it was not received, and what do we do at the client side? We retransmit it. And it works same way, client to server, server to client, doesn't matter. Okay, let's move on. Now what happens if some of the segments are received out of order? And what I mean by that is, what if the client sends 1, 2, 3, 4, 5? And what if the server receives 1, 2, 4, 3, 5? Notice they were out of order, 3 and 4. Well, it's not a problem, because each time information is sent, it has a sequence number, and then the destination can look at the sequence number and put them back in their proper order. You need to know that it does not say send it again. Oh no, it says no problem, I'll put it in the proper order. Okay, and then there's like this manageable data flow. Data flow is a new keyword. It's kind of advanced, so we're actually learning advanced topics so fast. But data flow says, hey, if the server can only receive a certain amount of traffic, don't send it too much. So the analogy I like to use for that is the following. Let's say you go on vacation. What's going to happen? Your mailbox, it's going to get filled up more and more and more. So what do you do when your mailbox is getting full? Let's say you knew it was getting full. It was like a huge mailbox, but your neighbor calls you and goes, oh boy, your mailbox is almost full. That would be like data flow. And what you could do is you could tell the senders of maybe like the newspaper that fills it up the most and say, stop sending the newspaper, I'm on vacation. So that's part of data flow. That's exactly what the computers do. They say, stop sending data. I'm like totally overwhelmed. I have too many newspapers in the post box. And then the other side will stop sending. How did we do that? It's via standards. There are standards so that everyone who writes the programs, it's all going to work the same way. You can have the sender and receiver from two different vendors, implemented code, and data flow will work fabulous because we have standards. And the data flow stops congestion, overloading, even data loss. If you receive too much traffic and you don't have enough buffers, you run out of data. Just like at home, if you have too many newspapers in the post box, it's just going to fill over the top, and it's just going to be totally done, and you're going to lose papers. People will steal them. Let's talk about details, okay? I mean, it's nice to see a picture, and this is an awesome picture. This is connection oriented, so it's TCP transported as opposed to UDP. And what we do is we send a sync, and we say SYN. We send the SYN, we negotiate a connection, we get a SYN the other way, we get an acknowledgement both ways, and that's SYN ACK. And then sooner or later, we're going to get a connection. Okay, we got a connection. All of that to get a connection. And then, for the life of the connection, which could be a minute, it could be a few seconds, or it could be a few weeks, the sender and the receiver can just go at it and send traffic back and forth, and it will all be reliable. And if any segments are dropped, they're retransmitted out of order, put back in order. Everything is taken care of, so we have a great reliable session, and the application programs don't need to write all this code themselves. Now let's talk about flow control. Again, this is a little bit advanced, but I really like the way the book covers it. Here we go. Look at this. We got 1, 2, 3. And what does the receiver do with flow control if it's getting overloaded? It says, oh no, I'm out of memory. My buffer is full. Please stop. Please stop. And then after it says stop, it's going to process. It's going to read all that information, deliver it to the application. It'll have its memory free again. And it's just like you get back from vacation, you empty out that mailbox, and you just say to the post office, go, I'm ready to get some more. So that's flow control. It works the same way the post office and the computers. So you notice after the sender received this stop message, it did not do anything until it received this message. What is this message? Oh, it's go. So go, and then it fires away. It's been waiting a long time, and then the newspapers just start flying into your mailbox again. That is flow control at layer 4. We have this other topic called windowing, and this is really cool. Instead of like just sending traffic and sending traffic until the other side says stop, wait, the receiver can say, I only want one newspaper at a time. I only want one frame at a time. And you know what's going to happen? The sender will send one frame, and then it will wait. Notice this time with windowing, sender 1 never received a stop. It just knew ahead of time that we have a window size of 1. So as soon as it sends 1, it waits. It's very patient. And then the receiver says acknowledge, and then this is a magic code here too. It says acknowledge, send me 2. And it doesn't mean the number 2 frames. It means send me the second frame. And then the sender will send the second frame. And since the window, again, is 1, it will not send 3 until it receives this, which is what? An acknowledgement that 2 is received. And it might look odd to you, go, acknowledgement, it says acknowledgement 3. It says acknowledgement that 3 was received. Well, that's not how the standard protocol works. What we do is we say acknowledge, and we say the next one we want. So the next one we want is 3, and then the sender will go ahead and continue. Now, down below we have a separate example, so don't you think that we're continuing with the same. So here's what we're going to do. We have a window size, not of 1, but this time of 3, and that means that the sender can have 3 outstanding frames that it sends. So what's it going to do? Oh, it'll send 1, 2, 3, and automatically wait. Again, it's not waiting until it gets a stop. It just automatically waits after 3 because we're using a window size of 3. What does the other side do? Same as before. It sends an ACK, which means I received at least something, and then it says which is the next frame it wants. It wants 4. What's the other side going to do? it'll send 4, 5, 6. Why does it send 4, 5, 6? Window size of 3. Why doesn't it send 4, 5, 6, 7? That would be 4, and we have a window size of 3. So that's flow control. It's not exactly the same as what we saw earlier with flow control. So we have flow control. It waits for what? A stop message. Okay, that's fine. But what about windowing? They agree ahead of time on what the window size is. So that is the difference between flow control and windowing. Now let's go into a little more detail on this acknowledgement. So here we have acknowledgements. We're going to go into a little more detail on that. We've got a sender and a receiver. And normally they're sending and receiving both, but this simplifies it. So here we're going to send 3. We get an ACK, we want 4. So it sends 4. It's got a window size of 3, for example. So what's it going to do? It's going to send 3. Now look at this. We can see 4 made it across, 6 made it across, but 5 did not make it across. Now notice this. It says connection lost. Now I'll tell you that's a mistake in the book. What I do before I give lectures is I read the whole chapter. And when I read the chapter, it said that it was just a lost segment. It's just only number 5 is lost. It's not losing the whole TCP connection. So ignore the word connection and think segment 5 was lost. But what if segment 5 is lost? Aha, we never received 5. We say acknowledgement, we received something, but what do we want next? We want number 5. And then we send that. We want number 5. The other side's very nice and kind. It sends number 5. Now check this out. ACK, we want number 7. What about 6? That's what I was telling you. Look, we received 6 here. So even though we didn't receive 5, we don't have to start and receive 5 and 6 again. We can just receive 5. We save a copy of 6, and then we ask for 7. So that's the beauty. And it works between any two vendors. You can have like TCP/IP software from 50 different vendors, and it's all going to operate, and this is how it's going to work. It's so nice to have these standards. Now let's talk about routing at layer 3. Now the first thing I'll say is the book has simplified the network addressing. I'm glad they did, but I just want to tell you they simplified it. Normally you have like A.B.C.D, and they only have like A.B. But I'm glad they simplified it, and here's why. For the way they simplified it, you can see there's 2 digits. There's a 1, and then there's a 0. The 1 up here, that's going to be the network number. The 0 is going to be the host number. Now what I mean by that is you could say that over here on the left, this is network number what? 1. How do I know that? Here we have 1 dot something. 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 You're getting the point. 1 dot anything is network number 1. That's right. Let's look for network number 3. Boy, I think I found it. Here's network number 3, 3.0, 3.0, 3.1, 3.3, 3.2, 3 dot anything. 3 is the network number. The dot whatever is the host number. Glad we got through that. Now let's talk about the routing table. Well, this is a router, and what we're going to do is build a routing table. Now the routing table is found in a router, but just so you know, routing tables are found in all hosts. They might be quite simplified, but they are there. So let's move on. This router, what is the job of a router? It's going to take traffic from the left, from over here, from the 1 network, and it's going to try to send it on its way, for example, over here to the 3 network. Now how does this router know? How does it know where to send the traffic? Oh, the routing table. So look at this magic here. Look at network number 3. Okay, that again is over here, network number 3. If I want to send traffic to 3, I go out my interface S0, serial 0, serial 0. So as the traffic comes in here from network 1, trying to go to network 3, it'll send it out its serial interface. Notice this router here, this router does not know all the details on how to get it to 3. All it knows and all it cares about is it's going to send it out serial 0. It'll get to this router, and then it becomes this router's problem to figure out the next step or the next hop to get to the destination. Now what's this router here on the right going to do? It's going to look at its routing table. For what? For network number 3. Here's 3, and what is it going to do with traffic for network number 3? Oh, it's going to send it out its Ethernet 0 interface, which is here, and that's exactly the correct network, and it's going to go on its way. Now just to reinforce that, I'm going to go really fast through another example, and what we're going to do is say, what happens if this machine wants to communicate with the top left PC over here? You know, what's going to happen? Okay, 3.1, it's going to use a destination address of 1.1. It goes over to this router, and this router looks up in the routing table. How do I get to number 1? It looks at 1. We got 1. We got a serial 0. So it's going to take this and send it on its way out serial 0 because this is the way to go. All is great. Oh, it hits this router, and this router says, what do I need to do? Oh, it's going to network 3. It jumps over its table. Router, network 3, serial 0. Oops, I'm sorry. Network 1, Ethernet 0. Ethernet 0, I got it on the way. Oh, bingo. That's how it works. I wanted to go through that really fast. So I think you're experts. The metrics, let's talk about the metrics. Metric says, am I directly connected? So network number 1, this router is directly connected through E0. So it says 1, E0, metric of 0, directly connected. Okay, that's all fine and dandy. Let's say it's trying to get to network 3. Is it directly connected? No. It's interface S0 and it's a 1, which means it's not directly connected. It's got to like hop over this router. It's got to make one hop to get there. Same vice versa. This router table, if it wants to get to the 3 network, here we go, 3. That's a 0, so it's directly connected out the Ethernet. That's great. But on the other hand, if it wants to go over here to the 1 network, we look at the 1 network, serial 0, that's how it's going to get there. That's right. Oh, metric 1, it's not directly connected. It's got to have the traffic hop over the next router. So that's the metric. Now we get it all. Okay, now we're going to talk about something new. We're talking about a broadcast domain. And here's the thing. We're going to talk about it later in the course, but a broadcast domain is a local area network. It's an IP segment. It's a single VLAN. So at home, when you have a whole bunch of machines, they're all in the same network, one machine may send a broadcast, an Ethernet broadcast, and all the machines on the same LAN will listen to it. Now here's a question to you. What do you think? If you do a broadcast at home, do you think that broadcast frame will go all over the world to every machine in the world? I don't think so. Why not? Oh, what happens is when it hits a router, each router interface is a broadcast domain, and it doesn't go from one to another. So if you have a router here, and there's a network on the right and a network on the left, a broadcast from this PC here will only go on its own local area network. Once it hits the router will not forward it to the other side. So we say the router breaks up the broadcast domains. That's what this is all about. Let's talk about the data link. This is really cool. At the data link, what do we got? Look at this. We have 2 different standards. Now the media access control, MAC, what we could be using is, for example, 802.3 Ethernet. We could also be using 802.5 token ring. And I wrote a book on token ring. It's got an ISBN number. But my advice to you, don't read any books on token ring. It's old. It's not commonly used. But the cool thing here was the following. There are a whole bunch of 802 standards. Just a whole bunch of them, like 802.3.5. There's just so many. And all of them will use the same protocol at the top. The protocol at the top, Logical Link Control, LLC. So think of it as like we have the same standards and protocol at the top, and it doesn't matter. We can change our physical interface down below from different types of networks, and it doesn't matter. the logical link control will still work the same way. Data encapsulation, I'm going to go through this pretty quick too. It's kind of like when you write a letter. You write a letter on a piece of paper. You take the paper, you put it in an envelope. You close the envelope, you put the address on it, you ship it off to the post office. Same thing here. We've got an email application at the top, and it's going to send data down. And when it sends data down, the next layer down may break it up into a bunch of pieces, but sooner or later, if it's a web application, the web browser is going to put the web server address on there. And at the layer 4, at the segment, it's going to put a, for example, TCP destination port number of 80, which is normally for a web server. And that is what we mean here by TCP header. It could be like the TCP header address and the source address. And then it'll also include, of course, the email message or the web request, etc. And then what's going to happen? Oh, this is really cool. Check this out. We're going to take the TCP header and also the upper layer data. And this big circle here goes into this little box here called the data. That's right. Everything here in the circle goes into data, and then we put an IP header. Now you might say, why do we need a TCP header and an IP header? But if, as I said before, the TCP address is 80 for the web server, whereas the IP address is going to be like the IP address of the Cisco server. And once it gets to the server needs to know, how do I get it to the web application? Oh, it looks at the TCP destination port number. And then again, we have to have some kind of MAC address, and the MAC address is local on the LAN, so even if we're going far, far away to the Cisco web server, we put the MAC address of our local home router. And just as before, you're getting to be an expert at this, just as before we have this big, huge circle, where does that fit in? Oh, into this little tiny data box. Just like before. I'll even do it again. You must be ready to kill me. That big thing goes in here, and the same thing goes again, and again, and again, and again. That's called encapsulation. That's all it is. And then, if you want to look it over here, we've got something called a protocol data unit. And at every layer we can say it has a protocol data unit. And just like I said before, the transport, we have a special name for the PDU, segment, network packet, data link frame, and then we have physical bits. So that's data encapsulation. Summary. Ooh, ah, hooray. We went through a summary, and I'll tell you, the book has a great summary you can go through. It has the exam essentials section, the written labs, the review questions. Oh, and while we're on the review questions, let me tell you something. The simulator has some awesome simulators where you can actually like configure equipment and do things. It also has quizzes, and what I've decided to do is, instead of like forcing you to try to do every single quiz question on the simulator, we're going to have a little change. I'm going to have you do the review questions in the chapter at the end of the chapter, and then that one's aligned more with the book, so it's going to go smoother. But I'm going to talk about it more because I do want you to be able to do some of the simulator quizzes, but we're mainly going to use the simulator also for the video presentations and also for the actual simulations where you configure equipment. There you have it. You asked for it, you got it. You wanted another tutorial, demonstration, presentation, whatever you want to call it, I've given it to you. I've agreed I'm going to give you 20. I'm going to go through every chapter, and I'm going to read every chapter before I give it so I can make sure there's no mistakes in the book. And then you'll have it, and the way to learn is to read the book, listen to my lectures, listen to my general talks, watch these videos, listen to and watch the videos in the simulator. So lots, and also Professor Messer, you can listen to him. So lots of ways information comes at you. Don't forget, work with your study partner. That's the best way to learn, to work with them, find out what problems he has or she has, and explain the answers, because by explaining you learn as well. That's it. Bye for now.